Good afternoon, everybody, or good morning, or good night. Maybe you're watching this at night. I don't know. But anyway, Unit 5, Day 7. Welcome, everybody. For those of you that are watching this lesson, you're either missed class or you're looking for that extra reference, all right? Or maybe you're just bored. Hopefully not the second option, right? Hopefully you're using this for some sort of purpose. But anyway, let's talk about what a series is. So series kind of ties in with our sequence part of this unit, right? When we're talking about, a list of numbers, either increasing or decreasing, either by an amount that's being added to, the same amount each time, or it's being multiplied from term to term by the same number, right? And so a series is just a sequence of numbers being added together. Whoa. Okay, and so what we're going to be doing is we're going to be taking these, referring to these same sort of sequences, these arithmetic or geometric, but instead of just figuring out the term number, we're going to be adding all the terms together, right? Okay, so just taking that concept of sequences and adding one more thing, right? We're adding all the numbers up now instead of just finding the pattern and whatnot. Okay, now an infinite series is a series which never ends. Okay, and so an infinite series would be, 1, 2, 3, 4, dot, 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 dot. Okay, goes on forever, right? And a finite series is just a series which does end. Okay, and we'll talk about the differences between both of those. Okay, they're not difficult to spot, but they do involve different things, right? They do involve, they involve a couple different things. So anyway, spotting them is not bad, but that's what you do with them is where we'll take that part of the lesson. So anyway, the first part is the warm-up, right? Find the sum of the following arithmetic sequence or series, okay? And so here's our our sequence, right? This is an arithmetic sequence, but now we're taking these numbers and we're adding them together, right? So let me rewrite this guy out. And let me put it like this. Make it a little artsy like, right? 5, dot, 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 dot. Okay, so there is our arithmetic series, right? Because we're not just finding the terms, now we're adding them all up. So get some different colors here. So 100 to 101, we add those together, or 1 to 100, add those together, it's 101. Okay, now let's add these two together. Okay, 2 plus 99, well, that's also 101. What about 3 and 98? Add those together. That's also 101. All right, 4 and 97, 101. 5 and 96, 101. Okay? Hopefully you're starting to see the pattern, right? What's happening here is when we add this guy to this guy, right, we get 101. When we add this guy to this guy, we get 101. And then when we add this guy to this guy, 101, so on and so forth. Okay? And so how many times do you think we can actually end up doing that? Right? Well, what happens is we actually end up doing that we actually end up doing that 50 different times. Okay? And so how many times are we coming up with 101? 50, right? So if we were to add all those up, right, 101 50 times, you would get 550. Okay? So what's happening is we're pairing these up, right? When you're pairing those up, how many pairs do we get out of 100? Well, 50, right? And so, add all those up, 1 through 100, we get 5,050 as a sum. All right, but a long, long time ago, someone came up with the formula for finding these guys here. Okay, so instead of doing something lengthy like that, okay, someone took the time for us to actually come up with some formulas. Okay, so instead of adding arithmetic sequences or arithmetic series up like that, okay, we're going to utilize these formulas down here. Okay, so the sum of a finite, okay, known as finite arithmetic series, all right, the formula for that looks like what I have circled there. Okay, the formula for finding a finite geometric series looks something like this. And then finally, the sum of an infinite geometric series looks like this. And when I say infinite, I mean that it's going on forever. So these two up here, all right, we'll talk about when those examples come up, but it's pretty easy to tell when we're talking about a finite series, right? Because they tell you what term that they want you to add up to, right? For these infinite ones, you know, especially for the infinite arithmetic series, which, by the way, does not exist, okay? Because let's think about this, right? Numbers go on forever, so if your sequence keeps going up, right, we just keep adding, you know, let's say we're adding 2, right? Well, you keep adding 2, adding 2, adding 2. How can we keep summing that up if numbers are infinite? Okay, same thing with this infinite geometric series, okay? This happens only if r, the actual number itself, is less than 1. Okay, and so we'll see an example of these down below where r is not less than 1, and you start to see what happens to these numbers. Okay, so anyway, let's get to number 1 here. Okay, so number 1 looks exactly like that example up top there, right? So instead of adding it like we did before, let's utilize the formula here. So the formula states this. So series always looks like this, some s of n, right? So that n is your term number. Okay. Again, a sub 1 is your first term. A sub n is your last term. Okay. And I think that's all we got, right? Okay. So s sub n is equal to n divided by 2, a sub 1 plus a sub n. Okay? And so in this particular problem, we do get all of these pieces, right? So how many terms are in the sequence? Well, we're adding 1, adding 1, adding 1 until we get up to 100. So if this is our first term, our last term is 100. Okay? So we're going to find the sum of these 100 terms, right? So anywhere you see an n, you're going to put the 100 because that lets us know how many terms are in the sequence, right? There's 100 terms. Now, what's our first one? First term is 1. Last term is 100. And we simplify this out. Lo and behold, what in the world do we get? We still get 50 times 101, which is 50/50. Okay? So somebody a long time ago figured out that, hey, I'm not adding these things up like this. I got this formula right here that I just figured out, and it works every time. And so someone found this formula, and it works. And this formula can be utilized to find the sum of arithmetic series. Okay? Finite arithmetic series, right? This one's finite in the sense that, as you can see, right, we stop after our 100th term. Okay? If you look down below in example 2, okay, they bring up this thing called partial sum. Okay? So partial sum ties in right with, well, what they describe it as in the first piece. So find the sum of the first 30 terms. Okay? So sometimes your regents will ask you to do this. Sometimes they'll ask you to do this, right? But 30th term or 30th partial sum, right, is the same thing. Okay? So they're letting us know that they want us to add the terms in the sequence all the way from our first term to our 30th term. All right? Now, when you go to look at the formula here, okay, you'll see that we're missing a couple things from this guy right here, right? We have 30, right? 30 divided by 2. Anywhere you see an n, you put a 30. And so a1 goes there. But we don't have this guy right here, right? We don't have our a to the nth term, or our 30th term. So how can we find that? This guy right here. We're going to have to utilize the formula from the reference sheet. Okay, so there's our first term. We're going up by 3 each time. So to find our 30th term, it's going to be 4 plus 3 times 30 minus 1. Whoops. Shrink this up here. Which is 4 times 29, or 4 plus 3 times 29, sorry. So 3 times 29, 87, plus 4, 91. The 30th term is 91. So we got everything we need. And so I just plug everything in here. So it's going to be 15, first term, plus 91. So 15 plus 95. Wish I had this much money. Nope. No, whoa. 15, huh? Find the sum. Right? Okay. Right? 15 times 95. 1425. Okay, I'm satisfied. All right, so that's the sum of all those numbers in that arithmetic series. Sequence. Series. Sorry. I always get them confused. My bad. I'll try to make sure I don't mess up like that, okay? So anyway, that is the sum of the first 30 terms from this, excuse me, from that arithmetic sequence, okay? All right, number 3. Same type of problem, okay? Except they're looking for the 19th partial sum, okay? So unfortunately, again, what we don't have, 19 divided by 2, first term plus a to the 19. We don't have our a to the nth term. So a to the 19th is equal to our first term. Looks like we're going up by 5 each time. 19 minus 1. Negative 10 plus 5 times 18. We end up getting 80 for our 19th term. Okay? And so now, I'm just going to plug that in. So S of 19 is equal to 19 divided by 2. First term is negative 10. So 19 halves times 70. 665. Okay? How many examples we got? All right, we're cruising here. All right, so those are finite arithmetic series, okay? And remember, there is no such thing as an infinite arithmetic series, because if you think about it, right, you can just keep adding numbers and adding numbers. So if it's infinite, well, that number is just going to keep getting bigger and bigger, okay? So the next two are also finite, okay, but they're no longer arithmetic. they're geometric. Okay, so as you can see, right here we're multiplying by 5. Here we're multiplying by a -3. Okay? But again, they're both finite geometric series. Okay? So the formula, correct me if I'm wrong, I think it looks like this. First term minus our first term times r raised to the n all over 1 minus r. Okay? Where r cannot equal 1, which makes sense because if our common ratio is 1, well, what the heck kind of sequence are we looking at then? You know what I mean? It's not going to be very exciting if our ratio is 1. No, there's our sequence right there, right? So, nothing exciting when your ratio is 1. So anyway, what's nice about this one, though, is all we need is our first term and what we're multiplying by, and then in this case, our term number, which is 10. Okay? So S of 10 is equal to our first term plus 1 times 5 raised to the 10 all over 1 minus 5. And when you solve that out, oops, 1 minus, sorry, hey-o. So 1 minus 5 raised to the 10th power, so negative 97, 65624, all divided by a -4. And we get, drum roll please, 2441406. So 2,441,406. And that is the sum of the first 10 terms of that geometric series. Okay? It's a geometric sequence, but again, it's a series now because we're adding them all up. Okay? Next one. All right, find the sum of the first 20 terms. Okay? Same process. So here's our formula. All right, so I'm going to substitute anywhere I see an n, I'm going to put a 20. First term is 2, minus 2 times our ratio, which is -3 raised to the 20th power, all over a 1 minus a -3. Okay, so on the top, I'm probably going to have to shrink this down here. All right, so we're going to get 2 minus 2 times a -3 raised to the 20th power. So up here, we get a negative, 697, 356, 8800, all over 4. Whoops, dang it. Hit the wrong button. Divided by 4, and our answer is a -17433922200. Cha-ching. There we go. All right, so actually the sum ends up being a negative number, right? Because if you think about it, even though we're multiplying by a -3, those numbers are getting really, really high towards the end. Right, so depending on what number comes up on top as far as the positive or negative there, right? Maybe that negative number at the end, that last number ends up being negative, which ends up being the largest one of the bunch, right? But anyway, it looks like we're going to end up getting a large negative number at the end. Okay? All right. The last two, okay, are infinite, all right? And they're infinite, and not only they're geometric, right? Because if you look at this one, it looks like we're definitely not adding the same amount each time here, right? Actually, it looks like we're multiplying by a negative 5/2. Okay. Now, if you're ever unsure on how to find what we're increasing by here, here's your method. Okay. Take the last term. Let me shrink it down here a bit. Okay. Take the last term. And then you divide it by the one prior. So this would be 32 divided by 125. When you do so, you end up getting a negative 2.5. Okay? And then this guy here, I'm going to go 32, 125, all that divided by a negative 64 over 625, and that's also a negative 2.5. But then if you're ever unsure, you're like, I don't know, what if they mess me up on that last one? Okay, 128, 31, or I'm sorry, hey-o, negative 64 over 625, all that divided by 128 divided by 3125. Make sure you guys are putting those in parentheses when you put them in your calculator. But again, you divide the fourth term by the third term by the second by the first, okay? And in all of those cases, we end up getting a negative 2.5, okay? Which lets us know that, because when you divide those out, that lets us know what we're multiplying by each time, okay? All right, so anyway, that's what we're increasing by. Now, here's the kicker, okay? Going back up to the top, it's got this special thing right here. It says if r is less than 1, okay? So when we're talking about the r, okay, we're talking about the actual number here. Even though we're increasing by a negative 2.5, okay, I'm focused at this guy right here, okay? And so let's just take this a step further and see what happens if I keep multiplying by a negative 2.5, okay? So 16 divided by 25, oh, I'm sorry, whoops. Okay, times a negative 2.5, we end up getting negative 8/5, okay? And multiply that by a negative 2.5. We're going to get a positive 4. And then multiply that by a negative 2.5. We're going to get a negative 10. Multiply that by a negative 2.5. We're going to get a 25. Okay? So no matter what, though, even though we're going positive to negative, this number towards the back here is going to get super large, right? Because we just keep multiplying by 2.5. So, that being said, all right, this series, all right, the sum of this series, okay, does not exist because 2.5 is greater than 1. Okay? So even though, it says up there if r is less than 1, we're talking about the actual number itself, the r value. Okay? So if your r value, positive or negative, is greater than 1, then that means that the sum of that infinite geometric series does not exist, right? Because this number here, right, as we keep going, 25 times negative 2.5, well, now we're up to negative 62.5. And then the next one is going to be, 156.25, right? So just going to keep getting larger and larger, right? And so you'll discuss these sort of things when you get into calculus, when we start talking about, series and converges and diverges. And this is one of the things they talk about, right? Is this number going to start getting, is what we're going to keep adding to the pile here, is that number going to keep getting smaller and smaller or larger and larger? In this case, even though it's going from positive to negative, that number that we're essentially adding is going to continue to get larger and larger. Okay, so therefore it does not exist. All right. Now, in this one though, it does exist. All right. What we're doing is we're actually multiplying, even though it's negative. All right, we're multiplying by a negative 1/3. Okay, so we're going from positive to negative, but we're multiplying by a 1/3. So 1/3, all right, is definitely less than 1. So what happens is, as we continue down the line here, right, so negative 1/9, okay, times it by a negative 1/3. Right, now we're down to 1/27. And then multiply that by negative 1/3. Now we're down to a negative 1/81. Okay, times that by a negative 1/3. 1/243. So what's going to happen here is these numbers that we continue to add here, because 1/243 is this number right here, right? 0.0041152263. And what's going to happen is these numbers that you're going to keep adding, multiply by that again. Right, now we're adding a negative 0.001371741, right? And so what happens is these numbers that we continue to add keep getting smaller and smaller. So that's why that R value being less than 1 really means something, because what happens is eventually these numbers that we keep adding are so small that they're not really changing. They're not really changing the number anymore, right? Because you can't really notice the change. So it's almost like your asymptotes, right? It converges on this value here, right? And it actually gets small enough to where like it's as close as it's going to get, right? This number can actually, this series can actually have a sum because it converges, right? It gets smaller and smaller. This number we're adding keeps getting smaller and smaller until that number we're adding is no longer really affecting our amount at the end, okay? So anyway, I'll try to explain that further in class when I have you, but hopefully that makes a little more sense, right? This R value, if it's less than 1, then this number we continually add towards the end will be so small that it just won't change the value of anything. So it actually converges on a value, right? And that's a calculus term, so those of you that decide to take that in the future, you'll run into that term again. So anyway, here's our first term, right? So this infinite series also has a different formula. It looks like this. S of n is equal to our first term over 1 minus r, if I'm not mistaken. Let me check to be sure. Yep. Okay, so it's going to be 3 over 1 minus our ratio, which is a negative 1/3. And when you find that all out, you end up getting 2.25 or 9/4. Okay, so in retrospect, what happens is we're starting at 3, and we add all these numbers up, and eventually that value, all these values end up converging so that it just converges to 9/4, right? As you keep adding stuff to it, these super small numbers just don't seem to affect this guy anymore. It just stays about 9/4 as you move forward, okay? And so that's what we're looking for. We're looking for this guy right here, the actual number, whether or not that is less than 1. Okay, so hopefully that makes sense, you guys. Any questions, please bring this to class. I'll put up an answer key for you guys here shortly. And have a good day. I'll see you guys